All right, our last video here to prepare you for your first test. Maybe some of the other ones were for test 2 or something, but let's just get through this. So the objectives here are to practice drawing and writing Lewis structures, calculating formal charges, and determining the best Lewis structure representation of a molecule. To gain familiarity with the different ways that organic molecules are drawn or portrayed, i.e. condensed structures and skeletal structures, and recognizing the presence of electron pairs that are not drawn or shown. All right, so part 1 here, Lewis structures and formal charges. The following exercises are to be done by referring to your lecture notes or textbook for guidelines to writing Lewis structures. The degree of difficulty is indicated by the number of stars shown in front of the exercise, 1 star being the easiest and 5 stars being the hardest. All right, so question A here is 2 stars. Complete the Lewis structures from the following molecular skeletons. Chloromethane, bam, 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 bam. 1, 2, 3, 4, 5, 6. So yeah, make sure to put in lone pairs. Carbon, 4 bonds. Chlorine, 1 bond. Hydrogens, 1 bond. Next one, we've got methanol. Carbon, 4 bonds. Oxygen, 2 bonds. Hydrogens, 1 bond. All right, and again, 2 bonds, 2 lone pairs. Try to make those always add up to 4 pairs of electrons. So no bonds, 4 lone pairs. 1 bond, 3 lone pairs. 2 bonds, 2 lone pairs. 3 bonds, 1 lone pair, like the nitrogen here in methylamine. And 4 bonds, no lone pairs. Sulfur here is 2 bonds, 2 lone pairs. Sulfur is in the same group as oxygen, so 2 bonds is pretty typical there. For methane thiol. For ethylene, we have the carbons connected there. You see they each only have 2 bonds, so give it a double bond. For formaldehyde, the hydrogens are bonded to the carbon. Carbon has 2 bonds, so it needs to have a double bond to the oxygen, and then the lone pair. All right, now we have acetonitrile. 1, 2, 3. If you connected everything with a single bond there, you see carbon on the left has 4 bonds. Carbon on the right only has 2. So there's the 3rd and the 4th bond. The nitrogen with 3 bonds is going to have 1 lone pair. And again, nitrogen wants to have 3 bonds, so this works out perfectly for that. Acetyl chloride. 1, 2, 3. Connect everything with single bonds. All right. Now you see that carbon on the right only has 3. The oxygen wants 2. It has 1. Chlorine wants 1. It has 1. So that's good. So give the double bond there. Don't forget the lone pairs to add up to an octet of electrons. And then formamide. Again, as they get more complicated, start with single bonds everywhere. Nitrogen wants 3 bonds, and it has 3 bonds, and now a lone pair. Carbon wants 4, it only has 3. Oxygen has 1, it wants 2, so give it a double bond. 2 bonds, 2 lone pairs. Now, by doing it this way, everything is neutral in this case. Every atom is neutral. If you were to be given the chemical formula like CH3Cl, you add up the electrons and you get 14. There's 2, 4, 6, 8, 10, 12, and 14. They're all going to add up correctly in this case. So the methodologies I have shown in class and everything, how to go from a chemical formula to a structure, those still apply. But when in this case, because you're kind of sort of given them already, just kind of do what I did here today, and it happens to work out properly. I wouldn't guarantee that it always does, but you also weren't given the molecular formula technically, but this was designed in a way to kind of guide you to the right structures. Now, the lone pairs might be the hard part because maybe you don't know sulfur, but you see there's CH3SH. It's got carbon with 4, plus there's really 4 hydrogens, plus the sulfurs in group 6. So again, this is going to have 14 electrons. And there's 2, 4, 6, 8, 10, 12, and 14. So it does work out. If you didn't have the lone pair on there, before you've drawn those on, count them up, you get 2, 4, 6, 8, 10 electrons. And you see the sulfur only has 4 electrons around it, so 2 lone pairs works out perfectly for that. And the rest of them will just kind of follow the same type of procedures to get the correct responses. All right, question B, 4 stars. The next one below has 2 good Lewis structures. We'll call resonance contributors. Draw both of them. Be sure to show lone pairs. Also be sure to show the formal negative charge on the appropriate atom, not outside the brackets like I did. Now, in this case, the negative charge outside the brackets indicates that this chemical is charged, and it has a negative charge in total. There could be a positive charge on an atom, but as long as the charges of all the atoms add up to -1, then it will be correct. So we have 2 hydrogens, 2 carbons, and a nitrogen. There's 2 plus 2 times 4 plus 5 electrons here. And a negative charge of 1, so we're adding 1 more electron. So we get 2 plus 8 plus 6 is 16 electrons. Just so keep that in mind. Connect everything together with single bonds first. If we were to give everything an octet, as shown here, and we added up the electrons, there's 2, 4, 6, 8, 10, 12, 14, 16, 18, 20 electrons. That's too many electrons. So, if instead of doing that, all single bonds, there's going to be double bonds and maybe a triple bond. So just to point out, we could have a triple bond here, which would give a lone pair on the nitrogen. And there's 2, 4, 6, 8, 10, 12, 14 electrons. But again, we're supposed to have 16, which now, there we go, that carbon now has an octet, and there would be 16 electrons. So maybe that's it. But it turns out, that carbon would be negative. Well, we could have a resonance structure there that moves a double bond, produces a double bond between the carbons, which will break a double bond here. So if I draw that, you get that structure there. And so those are 2 good Lewis structures. It's not to say there couldn't be others. I'm not going to go into that. But those 2 at least work. Now, I kind of jumped into that. So just if I were to go backwards, and that was, again, kind of just chance that it did that. But if we started with all single bonds and then lone pairs, we had too many electrons. So we could add a double bond here, or we could add a double bond here. And if we give everything an octet, because there's 2 bonds to the nitrogen, it needs 2 lone pairs. Because the carbon in the middle has 3 bonds, it needs 1 lone pair. And that carbon also needs 1 lone pair. In the left structure, the carbon on the left has 4 bonds, so nothing, no lone pairs. 1 lone pair on the central carbon, and 3 lone pairs on the nitrogen. Now are these good? And let's add up the electrons first of all. 2, 4, 6, 8, 10, 12, 14, 16, 18. 2, 4, 6, 8, 10, 12, 14, 16, 18. So they each have too many electrons again. Too many, in fact. So what you can do is just add multiple bonds. And by that, multiple bonds means like make a double or a triple bond. If I added another multiple bond between the two carbons, I would get that. But this carbon has 5 bonds shown, so that's not a resonance structure. Bam, that's gone. So instead, I could add the double bond between the carbon and the nitrogen. Count up the electrons. 2, 4, 6, 8, 10, 12, 14, 16. Now, when we do formal charges here, we'll see that the nitrogen is the negatively charged atom because you have it from group 5. You subtract the number of lines and the number of dots. 5 minus 2 bonds and 4 dots is 5 minus 6, so -1. The carbon has 4 bonds here. It has 4 bonds there, so both of those are neutral. All right, so that was, wrong here. And that was the only valid structure coming from that. If we go from the double bond being on the right, I could, again, make a double bond on the left, keeping the double bond here. And again, we get the negative charge there. On the other hand, I could make a triple bond by adding the other multiple bond on the right. That was negative, by the way, and this was negative. So, again, it's that one didn't work technically. But now I'm making a triple bond here, like that. The nitrogen is going to end up being neutral. The carbon will be neutral there, and this carbon will be negative. So we only can possibly get 2 valid Lewis structures. And again, I could make the triple bond here, pushing those up there to create that negative and that bond there. And those are the 2 valid Lewis structures. Which of the 2 do you think will be the major contributor? Well, first of all, the major contributor is always going to be the more stable one, so therefore lower in energy. All right, and then why? Well, if we look at the 2 resonance structures, every atom fills their octet except for the hydrogens, which have 2 electrons. So there's no difference in the total number of electrons, which is good. And again, we're going to follow Serio, looking at the negative charges. So let me fix, actually, let me get some of let me draw them down here. All right, so we get those 2 resonance structures, which there, if you want, put it all around brackets with a negative charge outside. Now, which one is the major contributor? We're going to follow the Serio. All right, again, size only works if there are 2 atoms we're comparing are in the same group. We have a nitrogen that's negative versus a carbon that's negative. So those are in the same row, not the same group. So we're looking at electronegativity. And the electronegativity of carbon is 2.55. The electronegativity of nitrogen is 3.04. So the nitrogen is going to win there. That one didn't matter. Resonance, this has resonance, but so does this. So I would say resonance is not an issue here. And then induction. Carbons are inductively electron pushing, so this carbon pushes towards the nitrogen, and this carbon also pushes towards the carbide, or the carbanion there. So induction isn't helping the issue. And then hybridization. In the nitrogen, there's electrons coming off in 1, 2, and 3 directions. So you have sp2, and the carbon over here, that's sp3. As far as stability is concerned, the sp2 is more stable than an sp3 due to the size differences, right? The sp2 is slightly smaller than the sp3, which is better. The electrons would be closer to the nuclei. The closer they are to the nucleus, the more stable they are. And therefore, the hybridization also gives us nitrogen. Negative charges are more stable. So there you go. All right, question C, compute formal charges in the following Lewis structures. I'm going to do this the quick way. Oxygen with 1 bond, 3 lone pairs is negative. Nitrogen has 4 bonds, it's going to be positive. Sometimes for these atoms, we say hydrogen is going to be 1. Lithium, sodium, potassium, those are also 1. We have fluorine, chlorine, bromine, and iodine also having 1. And I'm talking about covalent bonds they make. All right. And then you have beryllium is 2. Oops, I put that in the wrong spot. Boron is going to be 3. And I've run out of space, but carbon's 4. Nitrogen is 3, oxygen is 2. Those are the number of bonds, right? Sulfur will be 2 or 6. Phosphorus will be 3 or 5. Now, when we look at the number of bonds, like nitrogen here has 4 bonds. 4 is 1 greater than 3. So you see, it does work out here that 4 minus 3 is positive 1. For the oxygen, it has 1 bond. It wants 2. That's 1 less. And 1 minus 2 is negative 1. Now, the carbons, again, if we assume the hydrogens are being implied, right, there's hydrogens at these locations, then the carbons here, 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 and here will have 4 bonds, so their formal charges will be 0. So that's pyridine and oxide. Over here, again, we can ignore this. We're assuming the hydrogens are being implied. Now, oxygen has 1 bond, so negative, 1 bond, negative. Carbon here is 3 hydrogens and a nitrogen bonded to it, so that's 0. You have the sulfur in the middle. Sulfur can have 2 bonds or 6, which means that depending how you look at it, it could be like the 4 bonds shown minus 2 is a 2 plus, or it could be the 4 bonds shown minus 6, which would be negative 2. In this case, what you really want to do is look at the formal charge calculation. Sulfur is in group 6, and we're subtracting 4 bonds, and that gives us a 2 plus charge. So that's what we get there. The nitrogen has 3 bonds and a lone pair, so that one is neutral. All right, in phenyl isocyanide, again, we can ignore that part. We have nitrogen with 4 bonds, that's 1 more than it wants, so positive. Carbon has 3 bonds, that's 1 fewer than it wants, so that's negative. And I promise those work out. Let's see. Here we have, I guess it would be O-methyl tetrahydropyran. We look at carbon, it has 3 bonds, it normally wants 2. 3 minus 2 is positive 1. The carbon has 3 hydrogens and the oxygen bonded to it, so that's 0. The rest we can ignore. And then finally, the nitrogen has 2 bonds, 2 lone pairs. That's 1 fewer bond than it wants, so it's going to be negative right there. All right, and D, 4 stars. For the following compounds, draw a reasonable Lewis structure, show any non-bonding electrons, and indicate any formal charge on the appropriate atoms. Note both molecules are neutral overall. So we have trimethylamine oxide. So we've got 3 carbons plus 9 hydrogens plus nitrogen plus, let's put O for plus oxygen. So the total number of electrons, we've got 12 plus 9 plus 5 plus 6, so there's 32 electrons here. This actually is giving us a structure. We have an NO, and then it's giving us 3 methyl groups. All right, so I don't technically need or want to draw the complete Lewis structure, but it'll work out here as you see. So we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, and 32 electrons. I'm going to draw that out in a normal bond line or line angle drawing at the way we have it right now. Just with the, I don't know how the color changed there, but whatever. Here we go. Now nitrogen has 4 bonds, and so it's got 1 more than it wants, so positive. Oxygen has 1 bond, 1 fewer than it wants, so -1. Obviously, we could connect those together and make the double bond there, and you'd think you'd have everything neutral, but the problem with that is that the nitrogen has a double bond and 3 single bonds. It gives it 5 bonds, so technically, the nitrogen is violating the octet rule. So we can't actually do that, so this is what we get for that structure. And like I said, it is neutral. For here, diazomethane, one of my favorite molecules, we have 2 hydrogens, a carbon, and 2 nitrogens. So 2 times 1 plus 4 plus 2 times 5, we get 2 plus 4 plus 10 for 16 electrons. If you connect with single bonds, give everything an octet, you've got 2, 4, 6, 8, 10, 12, 14, 16, 18 electrons. So now connect them together with single bonds and give a double bond, either there or between the 2 nitrogens. Then make sure they each have an octet. So 1 bond, 3 lone pairs, 3 bonds, 1 lone pair. Carbon on the left molecule has 4 bonds. 3 bonds to that nitrogen, 1 lone pair. 2 bonds, 2 lone pairs. Now make sure you get the formal charges. The nitrogen here on the left molecule, here, let me just point out, that nitrogen here has 1 bond, which is 2 fewer than it wants. It does have an octet. This is another key thing to make sure you're doing, give it an octet. And since it has 2 fewer, it's going to be a 2 minus charge. If we look at its actual calculation, it would be 5 minus 1 bond and minus 6 non-bonding. 5 minus 7 is -2. The nitrogen in the middle has 3 bonds and a lone pair, so that is neutral. And the carbon is also neutral. If we add up the electrons, 2, 4, 6, 8, 10, 12, 14, 16, and 18. So that has too many electrons. 2, 4, 6, 8, 10, 12, 14, 16. What did I do wrong here? I didn't actually do anything wrong. I basically just took a lone pair and moved it over. This carbon there would have been positive. The nitrogen here would have been negative. So I didn't delete any electrons. I just moved them over. Whereas over here, this one does have the correct number of electrons shown because I have the double bond in a different position. That's how it works. But we end up with a positive charge here and a negative charge there. Nitrogen with 1 bond fewer than it wants It wants 3, it has 2, it's going to be -1. Carbon doesn't work for this. That's why I hadn't used an example that carbon has 3 bonds with no lone pairs. It's going to be positive. And then if there's a lone pair, that's where it's negative. Anywho, you get and overall it's neutral. That's diazomethane. But we could have a resonance structure here where we could put that lone pair and move it here. And then we get a double bond. Now we have that nitrogen still negative, and that one is positive. And that is a better resonance structure because this carbon has 6. And every atom in the bottom one has 8. So there you go. That is a better resonance structure. Although nitrogen is more electronegative than carbon, so you might see the positive charge in that carbon would be better than a positive on a nitrogen, but that's just not the case here because octet rule issues. All right, next page, condensed structures and skeletal drawings. In part C above, the structures are what we call skeletal structures. Like that. These line drawings are a shorthand notation commonly used in organic chemistry. In these types of drawings, the carbon atoms are not labeled, except sometimes terminal carbons, but are instead represented by bends or vertices in our line or by the end of a line, a terminal carbon. Hydrogen atoms are not shown at all unless they are bonded to heteroatoms, i.e. non-carbon atoms. A double or triple line represents 2 doubly or triply bonded atoms. We can think of the skeletal structure as being fully condensed, fully simplified structure. Sometimes structures are used that have lesser varying degrees of condensation or simplification. Below are 2 examples for you to study and think about. So we have these are the same molecules with the Lewis structure and the line angle drawing, or what they called here the skeletal structure. For each of the following molecules, A, count the number of carbon atoms and write it on the line beneath. 1, 2, 3, 4, 5. There's 6, because that's a hexagon, 7, 8, 9, 10, 11, 12. This is a pentagon, so 5, 6, 7, 8. 1, 2, 3, 4, 5. That was easy. 2, indicate on the drawings with arrows and hashtags and numbers the number of hydrogen atoms bonded to each of the carbons. Well, we have terminal ones will be 3 because the next carbon has a double bonded oxygen to it. It's not going to have any. And then these are 2 and 3. This carbon there needs to have 2 more bonds. It has 2 shown. Those 2 will be to hydrogen. The carbons here, 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 and here all have 0 because they've got 1, 2, 3, and 4 bonds shown to each of them. Like I focused on that one that I, circled there. And you can see a double and a single bond within the ring, and then the 1 bond jutting outward. So those all have 0. Then you've got 3, 3, 3, 3, 3. Because those show only 1 bond coming from them, so there must be 3 others to hydrogens. Any normal bend is going to have 2. Because there's 2 single bonds shown, so 2 others are the hydrogens. This one there has a double bond and 2 single bonds, so 0. Here, a double bond and 2 single bonds, so 0, and then 3 and 3 again. 3 and 3, because they're terminal. The ones in the middle with nothing else coming out are 2, And then this one is 0 since it has that double bond to oxygen. All right, C, determine the molecular formula of each of the following compounds. So first, let's count carbons. I'm going to do that in black. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So C14. Next, hydrogens. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, and 17. There's an oxygen, there's a sulfur, and there's a bromine. The order of those doesn't matter, by the way. Just get the right answer. Right number of atoms of each element. Just as far as enumerating the hydrogens on the carbons, this one has a double bond and 2 singles already shown, so it won't have any hydrogens. Same here, same here, same here, same there. And this one has 4 single bonds already shown, so those all have 0. All right, this one has a double bond and a single bond, so there's a hydrogen here, same with the one below it. This one will have 2, this one will have 1 because it has 3 singles already shown. And the terminals all have 3. That one in the middle will have 2, just like that one had 2. All right, let's count carbons. There's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33. All right, hydrogens. 1. Sorry, let's do that again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 24, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35. There's a nitrogen and a nitrogen. One, 2, 3, 4, 5 oxygens. And a fluorine right there. All right, part 3, finding lone pairs that are not drawn. In part 2 above, you may have noticed that we didn't show the lone pairs present on the heteroatoms. This is another shorthand that organic chemists use. However, it is very important that we always know how many electrons are present on an atom. We can know the number of electron pairs on an atom if we know the formal charge of the atom. The convention then is to always show formal charges and to leave out the lone pairs. This saves a lot of time by not having to draw a lot of dots as the lone pairs. For example, this is the same as that. You still have to draw the negative charge, so just leave the dots out. How do we determine the number of lone pairs actually present? 1, count the number of electrons the atom should have according to the periodic table. Take the formal charge into account. A negative charge means 1 more electron. A positive charge means 1 less, or 1 fewer, actually. And then 3, now you know the number of electrons the atom actually owns, or the molecule. Use this number to figure out how many lone pairs there are. Refer back to the equation for determining formal charge in the handout on writing Lewis structures. All right, study the following molecules. The alcohol here is the same as that, right? The oxygen, when neutral, is going to always have 2 lone pairs. When it has a positive charge, it'll have 1 lone pair. They need to have octets as well, so don't forget that. The nitrogen here will have 2 lone pairs. Needs to have an octet. Here, needs to have 1 lone pair to make an octet. 1 lone pair to make an octet. No lone pairs because it already has an octet. All right, final page here. For each of the following structures, draw in all the lone pairs. So carbon with a negative charge, in order to have an octet, you got to have that single lone pair. 4 minus the 3 bonds and the 2 dots, 4 minus 5 is -1. All right. Drawing in lone pairs, nitrogens, when neutral, will always have 1. When negatively charged, they'll always have 2. Oxygen, when neutral, will always have 2. You think about the periodic table, there's carbon, nitrogen, and oxygen, and fluorine. Carbon would normally have 0 lone pairs, nitrogen 1, oxygen 2, fluorine 3. All right. Nitrogen with 1 is neutral, but with 2, let me make a table here. If the number of lone pairs here, if it's 0, you have 4 bonds. The carbon wouldn't have any lone pairs. That would be neutral. If you have nitrogen with no lone pairs, it means it has 4 bonds. This would be a positive charge. Oxygen is not going to do that. It never doesn't have a lone pair. Same with fluorine. With 1 lone pair, the carbon is going to be -1. The nitrogen is going to be neutral. The oxygen will be positive, and then fluorine isn't going to do that. If there's 2 lone pairs, you won't see a carbon with 2 lone pairs very often, if ever. Nitrogen will be negative, oxygen will be neutral, and the fluorine, will it have 2 lone pairs ever? Yeah, I guess it could. If it had 2 lone pairs and a double bond, it would be 7 minus 6, so that would be positive. With 3 lone pairs, you're not going to see carbon with 3 if you didn't see it with 2. Nitrogen, you're not going to see with 3 lone pairs. Oxygen with 3 lone pairs is -1. Fluorine will be 0, and we're not doing noble gases. And then if there's 4 lone pairs, you're not going to see carbon, nitrogen, or oxygen, but you get negative on the fluorine. So you just notice that the negatives kind of follow that path, the neutrals follow this path, the positives follow that path, but you'll also see that in each row, let me change color here, you're getting -0 positive, -0 positive. You would have negative there for a boron with no lone pairs, with 4 bonds to it. And so it's a pattern that you could memorize. So you should be able to just look at these and say, oh, well, that's obviously a nitrogen that's got 2 lone pairs, so it's negative. The oxygen with 2 lone pairs, though, is 0 for both of those. And the nitrogen with 1 lone pair is 0. Just like, well, I don't have the one with the fluorine in there anymore, but if you have just fluorine with 3 lone pairs, if they're shown, then it'll also be neutral. All right. Hint, there's only 1 hydrogen bonded to this carbon. You shouldn't need a hint. There's a negative charge. That carbon's going to have a lone pair, right? 1 lone pair on the carbon, 3 bonds. The hydrogen is implied. You should just obviously at some point just know that. The oxygens are going to have 2 lone pairs because they have 2 bonds. Make sure they have an octet. All right, and then here this is saying, I think that's a different molecule below. Never mind. All right, carbon and carbon. So this is a lone pair here, and it's negatively charged, and that's it. All right, because again, one lone pair makes carbon negative. Nitrogen, to be negative, needs two lone pairs. Oxygen, 2 bonds, 2 lone pairs. Carbon has 4 bonds, so it can't have any lone pairs. All right, and then finally at the bottom, there's a lot of heteroatoms. Oxygen, negative charge, is going to have 3 lone pairs. If it's neutral, 2 lone pairs. Let's do all those. This one's neutral, so there you go. This one's neutral, neutral. All right, that's all the oxygens. Nitrogen with a positive charge. It's got 3 hydrogens and a carbon bonded to it, so it's positive, no lone pair. This nitrogen here has a lone pair because a double and a single bond. Double and a single bond there. The nitrogen here has 3 bonds to it, and they're all single, so 1 lone pair. A double and a single, and 3 singles. Next we have just the sulfur. It tells us it's a positive charge. So if we look at this, sulfur is also in the same group as oxygen. So it's looking like it would have 1 lone pair because that's when oxygen, it would have 3 bonds and 1 lone pair. Now here we do see 3 bonds, 1 lone pair. That sulfur gets an octet. Now, sulfur can be weird though, so let's count up the carbons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. All right, so we get C15. Now let's count up the hydrogens. All right, we're going to have 1 here, 2, 3, 4, 5, 6, 7, 8. There's going to be 9 and 10, 11, 12, 13, 14, and 15, 16, 17, 18, 19, 20, 21, 22, 23. Count up the let's do nitrogens. 1, 2, 3, 4, 5, and 6. Oxygens, we've got 1, 2, 3, 4, 5. And then there's a sulfur. All right, so we have 15 carbons, each with 4, 23 hydrogens, 6 nitrogens, each with 5, plus 5 hydrogens, each with 6, and the sulfur is a 6. They also are giving us a +2, so that's going to be subtracting 2. 60 plus 23 plus 30 plus 30 plus 4 electrons. But I forgot there's a negative charge there, so we're actually going to be adding 1 more. Okay, so we have 83 plus 60 plus 5. So we get 88 plus 60 equals 148 electrons. Now, let's count all these up. I gotta kind of erase all the color on there. And we have, I'm gonna put the lone pairs back on that I had drawn before. All right, so let's count up all of the lone pairs. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34. If we count up all of the bonds that are not to hydrogen. All right, so there's 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40, 42, 44, 46, 48, 50, 52, 54, 56, 58, 60, 62, 64, 66, 68. Now we do all the ones to hydrogens. So we get here 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40, 42, 44, 46. 34 plus 46 is 80, plus 68 is 148. So it does match up, which means you have that sulfur with one lone pair. That is the right answer there. Long story short. Obviously, I wouldn't suggest doing it this way, but just trying to show the whole story. And that is it for this document, and we're done with the videos here for now.